So let's continue on with our applications of exponential functions. We're going to start working on some exponential decay problems. So exponential decay is a situation where the amount of some substance decreases as time goes on, and there's less and less. Radioactive elements decay exponentially. Also, another kind of example is when there's a drug present in a person's body, the drug often breaks down in an exponential way. We're going to focus on radioactive element issues and problems and what we look at. The graph of an exponential decay function is going to look like so. This is the second page of our handout, and it's still that a0 e to the kt form of a function. What's different for exponential decay is the value of k is negative, and that negative value of k is enough to change the shape of the graph from what we saw for exponential growth and population growth. So we're going to start working on a problem now. I'll talk about graphs a little bit more after we get through all the examples. So example 4 is on the handout here. 100 gram sample of a certain radioactive element decays according to this formula. F of t equals 100 e to the negative 0.0018 t, where f of t is grams of the radioactive substance present after t days. So notice here my t value is, or my k value, sorry, my k value is negative for this function. It's negative 0.0018. And I think I just want to note down, so what we call A0 is 100, and what we call K, in this case for this function, is that negative 0.0018. So a negative K value is a signal that we're in an exponential decay situation. So let's start answering these questions. How many grams of the substance remain after 500 days? We just have to evaluate f of 500, which is 100 e to the negative 0.0018 times 500. Again, this is a calculator exercise, and I'm the one thing you do have to be able to do is you have to be careful to make sure you're entering a negative value. So when you take e to a power, you have e to a negative number. Here for my function value, I did this ahead of time, I get about 40.657 grams. Again, if you just said 41 or 40.7 would have been fine. You don't have to round off at 3 places. Part B, after how many days do 10 grams remain? So we got to find t for which f of t is equal to 10. So we're going to take our function. I just recopy 0.0018 t, and I'm going to replace f of t with 10. So 10 equals 100 e to the negative 0.0018 t. So to me, that almost the biggest challenge here is just trying to recopy k with the right number of decimal places, so be careful with that. And solve for t. So here we go again with isolating the exponential. we'll have 10 over 100 equals e to the negative 0.0018t. 10 over 100 is just 1/10, or 0.1. And take ln of both sides. The ln and e will cancel on the right, our shortcut, and I have negative 0.0018t equals ln of 0.1. So to solve for t, I have to divide both sides by a negative number here. ln of 0.1 is negative 0.0018 over negative 0.0018 is equal to t. And it kind of looks like we're getting, you'd think, are we getting a negative value of t here? But check this on your calculator. Enter 0.1, take ln, and then divide by that negative 0.0018. And you should get a positive result. I get approximately 1,279.2 days. So why does that come out to be positive? Well, if you were watching as you entered numbers into calculator, ln of 0.1 is negative. That numerator is going to come out to be a negative value because you're taking a log of a number between 0 and 1. A log of a number between 0 and 1 will always come out to be negative. So a negative divided by a negative is positive. And again, it should just come out, but if it looks funny to you, it's that ln of 0.1. In fact, 0.1 ln, it's like negative 2.3 approximately is the ln of 0.1. Okay, so let's move on to the next part of that problem, part C. And there are several parts to this question. Part C is how many days does it take for the sample to decay from 100 grams to 50 grams if we set up a table here, T, f of t. We know at time 0 we have 100 grams. And so if we want to know how long does it take to decay to 50 grams, to me it's like we're trying to figure out that t value. So we want to find t when f of t is equal to 50. And so I would solve 50 equals 100 e to the negative 0.0018 t. 50 over 100 is e to the negative 0.0018 t. So 50 over 100 is a half, or I could write that as just 0.5. And then when I take ln of both sides, well, it's just, the steps are just like what we just went through. I have ln of 0.5 is negative 0.0018 t. So ln of 0.5 over negative 0.0018 is going to be my value of t. And I believe I did this ahead of time, and I get 385 days is my value of t. So the question mark, what happened here? That's 385 days. And so let's continue on with the other parts of that problem. We also want to know how long does it take to decay from 50 to 25, 25 to 12.5. What I'm going to do is I'm going to just recopy this chart, this table, T, F of T, 0, 100, 385, 50, because what we can do is we can figure out the value of T that will give us 25 grams and 12.5 grams in each case. That won't be the actual answer to that question, but we'll be able to figure it out, all right, from that, because they actually want to know how many days from 385 to the next, from the next to the next. So let's figure out what these two missing t values are, again, for same function, f of t equals 100 e to the minus 0.0018 t. So if f of t is 25, solve for t, and I'm just going to tell you that I get t is 770, rounded off, and plug in 12.5 equals 100 e to the negative 0.0018 t, and solve for t here. And I won't write out the steps because we've gone through that so many times. I get 1155. So on my table here, I got 770, 1155, and I don't know if those numbers here, if you see a pattern there, but certainly it takes 385 days for the 100 grams to decay to 50, right? And for the 50 grams to decay to 25, what we got to do is we got to take 770 minus 385. That's 385. That's another 385 days. And to go from 770 to 1155, if we take 1155 minus 770, you get another 385. So that's the pattern here, the number that recurs over and over again. So the answer to part C is it takes 385 days for the sample to decay from 100 to 50 grams. 385 days to decay from 50 to 25 grams, and 385 days to decay from 25 to 12.5 grams. And this, if we go back to our handout here, there's a little statement after the problem. The 385-day period in the above example is called the half-life of the radioactive element. The half-life is the time required for half the substance to decay. This is the same no matter how much substance we start out with. So for our first 385 days, 50 grams of the substance decayed. But for the next 385 days, only 25 grams decayed. And for the third 385-day period, only 12.5 grams of the substance decayed. So what happens is that time period stays the same, but it's over that time period, the decay is always half of the amount that you had at the beginning of that time period. That's the half-life of the substance. So I'm going to stop this one here because I think we solved our A, B, and C of example 4, and put this up here a little bit more. And we're going to continue our word problems in another video.